Yeah, the first one.
All right, we've got our last mini quiz. Do I have the pencil? I do have the pencil. There's one over there by the microwave. All the way over here by the phone.
Yeah, 5 minutes seat. This is what, 5 minutes on this thing.
Well, you don't get to take your AP test there, so.
Well,
Yeah.
Mrs. Johnson, I have a question. Do we have to do a squishy rule?
You do whatever you want.
Okay.
Okay.
Can I just leave it like this? You have to simple.
No, you don't simplify. That's fine. So 2 points each. One's a multiple choice question, so that one's right or wrong. The other one, again, if you didn't hear me say that a second ago, you don't have to simplify it or anything, but it needs to be at least equivalent. Any way that you think that you can do that, it's fine. Okay, there's a couple things on the agenda that you can do while you wait for everyone else to finish. So if you want to turn it face down as you're done, that way I know when we can move on. But there is a Google survey I'd like you to do. It's like 5 or 6 questions. I think it's set up where each question is optional, so you can just answer the ones that you've got input on. But today is the last day I see y'all before your AP exam, by the way. This is a B week. So I want to get your input about how you felt about what you thought you would do on the AP exam before the school year started, now, right before, and then I'll ask you again after. Some of that same stuff I shared about with my classes from last year. It's the same survey that they took. And again, that's really short. But as I get your mini quiz, if you want to go ahead and pull that up and answer that for me. And I will be collecting the 140 circuit from last class. So if you don't have that finished, you can go ahead and start on it. But I would like that. Y'all had plenty of time to do that last time, so. I need that today to give you some points. Then I've got a 20-minute video I'd like to show you, and then I'll talk about the last 2 handouts you picked up and what you should try to get out of them. think we've got one more mini quiz we're waiting on. So again, if y'all would please do that Google survey. Shouldn't take you more than 2 minutes. Very short.
There's 140. Thanks.
Okay, anybody still working on the mini quiz? All right, let me go ahead and talk about class for the rest of today. So again, I've got 2 things that you can do here in just a second, but I'll put those back up. I guess you don't really have to do them at the start of class, but I would like you to do that Google survey. Again, it gives me some input based on, just how you felt going into the test, maybe some adjustments for next year's group. Try to, sometimes from my side, I see things different than y'all, so I appreciate your input there. And the circuit from last class. So again, I don't know why you wouldn't have that finished from last class, because I think you had plenty of time, but if you didn't finish it, go ahead and prioritize that and get it finished up today. I've got a 20-minute video I'd like to show you in just a second, but first let me speak on the 2 handouts. So again, this is the last day I will see you guys, so these are the last 2 handouts I have for you. I will try to put in a couple more grades after the AP exam, but it'll be stuff that you have done before the AP exam. So I'm not going to work you to death or anything. We'll be close to the end of the year anyway. But number 143 is one more handout where I tried to find 10 more points for you on the AP exam. So that puts us up to 5 of those type of handouts. Now, I had a list of other stuff that I wanted to put on them that didn't make any of the 5. But again, I wasn't aiming for trying to tell you everything that you need to study. I was trying to get you to section off and try to maybe gain close to 10 points or more than 10 points with each one of those. And of course, based on the past scores that they've shared with us the last 3 years, or the last 3 times that they've done that, 50 points would be enough to pass. So with that in mind, the other handout you picked up is what I call the survival guide, and it's got some information on there that's important. Some stuff that I have not even verbalized to you yet. So it talks about stuff that you should consider about before the exam, during the exam. It shares the testing schedule, just like what section comes first, how long, what section comes next, how long, just so you can be mentally prepared. But some of the stuff is like making sure your calculator's in radian mode, because everything we do in calculus is in radian mode. So if you have your own calculator and it is accidentally in degree mode, either A, you're going to be really confused on some questions because your answer's not going to match any of them, or B, even if you figure out it's in degree mode, it might be too late and then you're rushing around. So again, I'm not going to read all of those things to you. This is just one place that you could glance at, the day of the test or the night before the test, and be able to see that. On the second page of that though, this one might be the most important. This is some of the stuff that you could review, and I tried to prioritize what I thought was most important. So first, I talked about the 10-point closer handouts, because that could really get you to 50 points or more. Second, I talked about the 2 FRQ types that the Brian Passwater had told us was always on the AP exam. Number 3, I talked about the other 4 common types, or other 3 common types. And I remind you where you can access all those FRQs on the class website. Fourth, I remind you, make sure that you know all the basic derivatives, integration, quotient rule, product rule, all the formula type stuff. And the last 2 pages on this is, I didn't make this up, but just like a review sheet that's got that kind of stuff on there. Trig derivatives, inverse trig derivatives, speeding up, decreasing. This is the stuff, definition of a derivative. This is the stuff that I consider that you really want to know and have memorized going into the AP exam. So again, you should know all that already, so it should mostly be a matter of just going through and checking all of it off, but some of it you may not remember, so I would put that somewhere in my to-do list. And then finally, everybody's got different weaknesses, so I listed off a bunch of things that I thought were helpful, and again, they're completely optional. But AP Classroom, you guys had 1 mock exam, but I've unlocked 2 others if you want to practice more in the AP Classroom type of thing, like mock exam type of situation. I got the link to Khan Academy AP Calculus. You don't have to have those assignments assigned to you for you to go and practice those if you want to. There's a website, Paul's Online Notes, that I know are on my class website, but great practice with solutions and help and worked out and stuff. So if there's a skill or 2 you need lots of practice with, that's probably there. The AP Live videos. Do y'all watch the AP Live videos for any of your other AP classes? Do your teachers talk about them at all? No? Okay. So College Board pays a couple people to make videos, and they're usually like topicked. So like there'll be a video on limits and it'll be like 20 minutes long, and then a video on basic derivatives and it's 20 minutes long, and then a video, like basically each unit they just do a quick little summary. But those aren't random people, they're both I mean, they're not just hiring random people. They're hiring people that they know what they're doing. So anything that they're talking about is probably good refreshers. So I linked both this year's videos and last year's videos. And the lady who does them, her name is Verge, and she's actually made most of the circuits that you guys did this year. So she definitely knows what she's talking about. Maybe suggested looking at the when you see this is what you do. So I tried to mini quiz you on the first 2 pages of that, but looking over the last page and making sure you know those would not be a bad idea. And then I even linked some flashcards. Next page, I have a breakdown of the units and how much they weigh, if that's interesting to you, if that means anything to you. And then again, the last couple pages are just reference sheets of stuff that they expect you to have memorized. So I've tried to put that in one nice, neat place for you. So again, this is just something I would glance at for ideas on what else to practice, things to consider the day or 2 before the exam, things to think about during the exam, all of that kind of stuff. Okay, so before I give you time to look at that, my video is there. I have been actually lying to you guys all year long about something. So we spent all year doing calculus, but it turns out that you can learn all of calculus in just 20 minutes. So there's a kind of a funny video. It's silly, at least, where this guy, Professor Berger, tries to summarize all the important stuff in calculus in 20 minutes. So I'd like us to watch this, and of course all of this should sound familiar to you, and it gives you just kind of a good overview of the stuff that we have done this year. And then I give you the rest of the time to work through that stuff.
So we have to run really fast, go through the whole course. Let's begin. The first.
Oops, sorry.
All right. So now we're going to try to do the impossible. We're going to try to do all of calculus in under 20 minutes. So we have to run really fast, go through the whole course. Let's begin. The first 2 basic issues of calculus. 2 big questions. What are they? How do you find instantaneous rate of change? How do you find how things are changing instantly? And then, completely separate from that, how do you find areas under curves? 2 completely different questions. Turns out answers are completely related. Let's see how they go. Question 1. Instantaneous rate of change. What are we going to do? Well, what you do there is you first remember what is rate. Well, rate is just change in distance over.
What are you guys working on?
I was confused about the circuit that I missed last time.
Okay, worry about that after, because I want you to
Change in
listen.
time is as easy as that. Distance equals rate times time. Not a big deal. Okay, now what do you do with that? Well, if you graph a function that represents sort of distance against time, then what do you notice? If you want to look at the change in time and the change in distance, what do you got? You actually got a slope of a line. Right? This is slope, rise over run. Change in distance over change in time. Distance over time. So you got a slope. So automatically we see a really neat thing. We see that the average rate of change between 2 points is equal to the slope of the line connecting them. Well, that's really cool. By the way, what about lines? Maybe you got lines. Remind you about lines. Okay, no problem. We can do lines. We can do lines. Lines. Y minus y1 equals m times x minus x1. This is the point slope form. All you need to give me is a point on the line, x1, y1, and a slope, m. You give me those 2 pieces of information, I can always write down the line uniquely. Always. Never forget it. Okay, fine. Now we're back here. Now we can find average rate. And what do we see? Well, in fact, a line that touches the curve at 2 points is sometimes called a secant line. So in fact, we just discovered that the average rate, change in distance over change in time, is equal to the slope of the secant line. Cool. So all you have to do, want to find average rate, connect the 2 points to the line, find the slope, you got the average rate. No biggie. But that's not what we want. We want instantaneous rate. So how do you do that? Well, what would that be? Well, if I want to find instantaneous rate here, what would I do? I'd make that secant line closer and closer, bring these points together, and look what I'm converging to. I'm coming to a tangent line. Wow. Instantaneous rate of change equals the slope of the tangent line. So we want a slope of the tangent line. Well, what's the slope of the tangent line? Change in y over change in x, change in distance over change in time. But now the change in time from that point to itself is 0. 0 over 0. So I'm getting 0 over 0, which is complete garbage, and that is a big problem. Our first major problem of the course. Okay, so what do we do? Well, we can that. Distance equals rate times time. We're going to can that. Instantaneous rate of change, I really want that. So what do we do? Well, how do we get that 0 over 0 problem to go away? The answer is we inch up to it. We just approach the 0 point. And what would that look like? Well, let me remind you what you've done when you were a little teeny kid. When you were a little teeny kid, this is what you're looking at. You're looking at a value of function at a point. Value of function at a point. Okay, not a big deal. There it is. F of A, it's that point. But you don't know anything else about the function. You don't know what's going on around there. All you're looking at is F of A. You open it up. Woohoo! Function be quite interesting. Who knows? Okay, but now what I invite us to do, and what calculus invites us to do, is to look at the function this way. Cover up that point and look at everything else. Open the window, look outside. That's where calculus is. And what you see here is we can see what things are approaching, and we can actually determine the idea of a limit. The limit is what things are approaching. We don't care about what actually happens at that point, only what things are approaching. Armed with the idea of a limit, what can we do? Well, now we can return to the question and figure out. Let's take the limit as delta t goes to 0. What do we get? We get 0 over 0. That is called an indeterminate form when you get 0 over 0. So what do you do? You've got to do some algebraic gymnastics. You've got to factor the top and cancel with the bottom. You can try to multiply by the conjugate. You can try to combine the fractions. There's all these tricks in the trade to actually reduce this to something you can actually find. So find the limit. Okay, well, once you find the limit and you take the limit as delta t goes to 0, what do you get? You get the answer to the question. How do you find instantaneous rate of change? The answer is what we call the derivative. And what's the derivative? It's the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Looks pretty confusing, doesn't it? It's just rate. It's distance over time. But now I'm letting time go to 0. Not a big deal. So that's the derivative. Bingo. We're done with the first question. And so now what do we see? What we see now, that we come back here, and the derivative, in fact, gives us the slope of the tangent line. Well, that's really cool. If you want to find the slope of the tangent line ever in life, you just take the derivative. And that gives you the slope of the tangent once you evaluate it at the point you want. Great. But for free, we answer the first question. Because remember, the derivative also represents the instantaneous rate of change. So you want to find out how things are changing? No big deal. You take a derivative, plug in, and that will tell you how things are changing at that instant. Okay, great. So now we know all about how to graph these things, how to look at these things. The derivative is velocity, boom. We got all the way. Now let's take a look at some applications. What can we do with this? Well, how would you take derivatives of complicated functions? Well, if you got a product, take the product rule. Remember the product rule. Don't memorize the formula, memorize the chant. First times the derivative of the second, plus the second times the derivative of the first. So the derivative of product is this. It's not the product of the derivatives. You got to use the product rule. We got 5 minutes to stop here, folks. I got to move faster. What if you have a quotient? Well, then use the quotient rule. And what's the quotient rule say? If you got a quotient, you take the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. That's the quotient rule. That's what you use when you have a derivative of a quotient. Great, no problem. Now, what if you have a really complicated function? Well, you got a function just like this. It's got insides. It's got guts right in there. So you've got something like this, and you want to take the derivative of that. What do you do? Well, you got to use the chain rule, folks. This is a thing that you can chain together. There's an inside, there's a block right here, there's a whole big block there. And then you've got an outside. To take the derivative of the outside, the derivative of sine of blob is actually cosine of blob. So it's cosine of blob, and what's the blob? The blob is going to be 3x cubed plus 1, and then you multiply that by the derivative of the inside. And the derivative of that turns out to be just, let's see, 9x squared plus 0. And so there's the derivative using the chain rule. The idea is to peel off like an onion. Just peel off, keep peeling off the outside until you get to the inside. Always remember though, when you take the derivative, it's if you have sine of blob, the derivative is cosine of the blob. Don't put the derivative in there. Put the blob and multiply by the derivative of the inside. That's the key to the chain rule. Now we got the chain rule. Okay, what about when you have functions that aren't functions? Like what if you have things that are relations? Like x squared plus y squared equals 1, like a circle. How do you differentiate that? How do you find dy dx there? Well, the answer is we use something called implicit differentiation. Implicit differentiation. How does that work? Well, you've got to remember that dy dx, that's an object, that's a noun. And d dx is a verb. It's a commandment. Take the derivative with respect to x. So you differentiate this with respect to x. And what do you see? Well, you see something like this. What you do is you say, okay, I'll take d dx of x squared plus y squared equals 1. The derivative of x squared with respect to x is just 2x, not a big deal. The derivative of y squared, remember how I think about this? I think about this as clumping all this together. And I see this as a blob squared, so I actually use the chain rule which we just developed. And the chain rule says the derivative of blob squared is 2 blob, and then I multiply that by the derivative of the blob, which is the derivative of y with respect to x. That's called dy dx, folks. The derivative of 1 is 0. And now you can actually solve this for dy dx by bringing this to the other side. That'd be a minus 2x, you divide by the 2y, and you see dy dx equals minus x over y. And there's the answer. So that's implicit differentiation. Just go right through and differentiate implicitly. When you have a relationship, you can still find the derivative. Great. We're making progress here, folks. We are cutting through this stuff. Well, now that you have derivatives, what can you do with that? Well, if you think about it as a velocity, you get instantaneous velocity. If you take the derivative of velocity, you actually get the change in velocity, which is acceleration. So we get acceleration now, we get velocity. Acceleration is just the second derivative of the position. So we can actually take derivatives upon derivatives upon derivatives as many derivatives as you want. So it's great. We can do that. So higher order derivative, no problem. What can you use these things for? Okay, we know it's true for velocity. We can use it for velocity. What else can you use it for? Well, it turns out you can use it for linear approximation. Suppose you got some wacko function. You got some wacko function like this, woo! And you actually want to figure out the value right here, and you don't know. You don't know what that value is. But you know nearby there's a point that you can actually compute. So what do you do? You find the tangent line approximation because you remember the tangent line closely emulates the activity of the function. Tangent line closely emulates the activity of what the function is doing. They look the same there. So you find the equation of the tangent line and then plug in the mysterious point. Then you're all set because you can approximate the value by plugging into the tangent line. So how would that look? Well, that's called linear approximation. Here's the formula, but don't bother memorizing it. Just think about it. What you've got to do is you've got to find the equation of the line that's tangent at the known point, which is x here in this case, and this is going to be x plus delta x. The known point plus little t offset is approximately equal to the derivative times the change in x times the function. Plus the function. So that's it. That's the whole thing right there. Linear approximation allows you to actually compute things. Computers actually work this way. Computers know calculus. Everyone knows calculus. You've got to know calculus. Okay, now, what else can you do? Well, suppose that a derivative were to be zero. Well, how could that possibly happen? That could possibly happen because maybe the function goes like this, and I see the tangent over here has slope 0. Or maybe the function goes like this, and I see the tangent has slope 0. In particular, if tangent equals 0, maybe we have a max or min. Also, maybe the slope or the tangent doesn't exist. Like if we have a wave kind of thing, a cusp, very pretty cusp like the waves. Well, that might be a max, that might be a min. So in particular, you can find out when objects are maximized or minimized. You can find the maxima or the minima very easily by using calculus. What do? You take a derivative and you see where it equals 0. Or where the derivative doesn't exist, but the function does. Those give you candidates for possible max and min. And what can you use that for? Well, you can do all sorts of max and min problems. You want to maximize profit? You want to minimize costs? Oh my God! 20 minutes? No. It's only 10 minutes left. They're trying to fool me here, folks, but I'm not going to go up for it. 10 minutes left. Okay, so you want to maximize cost, you want to minimize cost, you want to maximize profit, you want to maximize area, you want to minimize volume, whatever it is, set up the problem really carefully, figure out exactly what you want to optimize, take the derivative, set it equal to 0, solve, find out where the derivative is undefined, and you've got it made. Really not a big deal. However, you should always remember and never forget the fundamental method of solving problems. So remember how you solve all of life's problems. The first thing you have to do is understand what you're being asked. You can't answer a question that you don't understand. The next thing you do after you understand what you're supposed to find, what you're being asked, is figure out what you know. List every single thing that you know, every single fact. Maybe it's superfluous, maybe you don't use it, who cares? Write it down, understand it, make it your own. And then the last thing is, take the information that you know and see a relationship between that and the thing that you see. Try to find a connection. Once you got a connection, then you're on the road to actually find a solution. That is a simple method for finding any single answer to any single problem. Another application, if you think about derivative as a rate, is looking at related rates. Suppose, for example, that you actually have a ladder, for example, that's falling down. The ladder is falling, and you don't want to be sued, but the only thing you do know is how fast the bottom is falling, you want to know how fast the top is falling. What you need to do there is, if you know this rate, you can find that rate by linking them up with a connection. In this case, the connection would be the Pythagorean theorem. You could take the derivative with respect to time, because here you see the variable, the thing that's independent, that's always changing is time. Time keeps on ticking into the future. So you keep on this, you actually solve this, take the derivative using implicit differentiation, differentiate with respect to time, and plug in what you know how this is changing, and that tells you how this is changing. Pretty cool. That's called implicit. That's called related rates. Suppose, for example, you drop a stone into a very still pool. You have a ripple effect that's making concentric circles that are getting larger. If you know how fast the radius is changing, you can find how fast the area is changing because you have a connection between area and rate. Area equals pi r squared. So there you go. Related rates. You know how one rate is changing, you can find out how a related rate is changing. Okay, what else can you use the derivative for? Well, the other thing you can do is actually graph really accurate pictures of functions. finally, you can figure out that a parabola looks really pretty and bowl-like, like this. And it's not something really exotic, but just a nice pretty bowl. How do you do it? Well, you just start taking derivatives and analyzing things. First, you find the critical points. Those are points where the derivative either equals 0 or the derivative is undefined, but the function is defined. So, for example, in these examples right here, you'll notice that the derivative equals 0 here, the tangent is horizontal right there, the tangent is horizontal here. In this example, the tangent is horizontal here, and then where does the derivative not exist? The derivative doesn't exist here, the derivative doesn't exist there. Those are candidates for maximum, those are called critical points. Then what do you do with those things? Well, you set them up on a little number line on the x-axis, and you look at the intervals all around it, and you see whether the derivative is positive or negative. If the derivative is positive, that means slopes are positive, so the function must be increasing. If the derivative is negative, then that means the function must be decreasing. So you can see that the function, for example, here is decreasing, then increasing. Here you can see it's increasing, then decreasing, then increasing. So you can see where it's going up and where it's going down by the sign of the first derivative. That also determines whether you have maxes or mins anywhere, and that's called the first derivative test. Now, how do you figure out the curvature? The curvature is given by the rate of change of the derivative, how the derivative is changing. So what you do there is you take the derivative of the derivative. So you look at the second derivative, and with the second derivative 0 are potential points of inflection, points where the concavity changes. This is concave up, it's curving upwards. This is concave down, this is concave up. So the cup is sitting up, the cup is sitting down, concave down. So here you would see the second derivative is positive, then the second derivative is negative, it changes here, now it's sitting up, positive, we're concave up. Here we're concave up, second derivative is positive, now here we see it's concave down, second derivative is negative, and second derivative here is also negative. This is a cusp point, the derivative doesn't exist there, this is a point of inflection, this is a point of inflection, this is a point of inflection, and that's a minimum. So just by taking derivative and then second derivative, you can actually figure out and graph a very accurate sketch of even very complicated, almost scary looking functions. By the way, that fractional exponents expect cusps. That's my word of warning for the day. Okay, now, if you got really exotic functions that have denominators, then actually we have asymptotes. So don't forget that a vertical asymptote is where the function, after you simplify it, the bottom equals 0. So wherever the bottom equals 0, after you simplify and reduce, those are going to give you your vertical asymptotes. Horizontal asymptotes, you take the limit as x goes up to infinity, as you go up to the horizon, and you see what y value you're trying to land to. If you're landing somewhere, then you know you've got a horizontal asymptote, and y equals that value. So you put in the asymptotes, and then you can do all the other calculus, get the curvature, see exactly what the view picture looks like. And that was the end of differential calculus. Great, no problem. Now what? Well, now we move on and look at the exact same thing we just did backwards. So we look at Math Jeopardy. Oh my goodness, I have only 5 minutes left. So Math Jeopardy, here we go. So the idea is, if I tell you what the derivative is, how can you find the function whose derivative is that? Well, this is the notion of an antiderivative. So how do you actually find antiderivative? Well, we saw the formula for that. If you want to find the antiderivative of x to the n, it would be x to the n plus 1 divided by n plus 1. Take the derivative of that, so you get x to the n. Unless n equals negative 1, then you're looking at the integral of 1 over x. And what's the integral of 1 over x? What's the natural log of the absolute value of x? Because the derivative of natural log we already saw was 1 over x. So great. Now, how can you find exotic integrals? Well, remember that d dx represents differentiating with respect to x, and so therefore the integral with respect to x represents to integrate with respect to x. Now, if you have a very complicated thing there, with an inside and outside, you might be able to untangle that, which potentially was made by the chain rule, by using substitution. Let u equal some big block, and the big block's derivative should appear somewhere else in your integral. If you've got that, it sounds like a good candidate for u to use substitution, and then you've got to change the dx to du by taking derivatives and seeing what du equals in terms of dx. So that's the u du substitution. You got that going on here. And now what do? You can take that and look at studies of motion again. Now I can give you acceleration. If you integrate, you get velocity. If you integrate again, you get position. So vertical motion, not a big deal anymore. Lands, no problem. Things moving in space. Like this thing here. Watch it go. You can get that. Anything that moves, anything at all that moves, we can now analyze whether you have crabs or whether you have a bike. It's not a problem anymore, folks. If it's moving, we can differentiate and figure out what it is. Not a problem. Now, where does this lead us? Well, it brings us back to the very first question of the course, which was how do you find areas under curves? You have to answer that. We haven't done it yet. It turns out the surprising answer is that it's the fundamental theorem of calculus. And the idea is if you want to find the area under this curve from A to B, right here, if you want to find that area, then how do you do it? It turns out that if that function is called, let's say, f of x, then all you do is integrate from a to b f of x dx. Because you're summing up little rectangles in here that are base, small change in x, base times height, which is the function you go from A to B, and this equals f of capital F of B minus capital F of A, where what's capital F? That's the antiderivative. So if you take the derivative of capital F, you actually get little f of x. So just find the antiderivative, plug in the big point, plug in the small point, subtract, that will always give you the area under the curve. You could look at the areas of more exotic things. For example, if the thing actually goes like this, then actually, this is actually not very x easy. The rectangles aren't very clear. The rectangles change from going from green to green, over to green to orange, and to orange to orange. It's not very uniform. However, if you put the rectangles in this way, and stack them this way, now you're summing with respect to y. And so here you would actually sum this with respect to y, so you would integrate this dy, and put the rectangles in this way, you put the rectangles in that way, and stack from low to high, and you stack the rectangles like this. Okay, that is all of calculus. I did it in under 20 minutes. That's what it is. Go back, think about it, have fun with it. Congratulations, folks. You just finished calculus 1. Have a good time, celebrate. Good luck in the final. Bye.
All right, so what do you think? Could you keep up with everything he was saying?
Absolutely.
Yeah? Should all sound familiar at least, but. Alright, let me put that agenda back up there. Again, this is the last time I see you guys before your AP exam, so obviously if there's something I can help with, then please let me know. It's going to be a lot easier to ask me for some help than it would be to figure it all out on your own. I guess before I completely go quiet here, this was one of my favorite memes of the year too. I just forgot to show it to y'all earlier. Thought it was pretty clever one. Where's the n at?
It's dn, so
Yeah.
Esper is a constant that begins at Mr.
Yep. And then the plus c, of course. Okay, what question do you have?
So about the circuit,
Yep.
I'm wondering how do I find the y value for these points to do my sum?
Well, this is the function, so you got to think about where you want the y values to come from.
Oh, so I just plug the numbers in?
Well, if this is -1 to 4, that means the total horizontal distance is 5. So if you're dividing it into 5 equal parts, each one has a width of 1. And if you want why that doesn't say where you should be plugging it. I think I must have done left Riemann sums, even though it doesn't say. So like when x is -1 would be the left side of the first rectangle, so I just plug -1 into this to get the length.
Okay.
And then the next one would be at x equals 0, so I plug 0 into this to get the length.
Okay.
But I don't like how they did that.
Mr. Townsend?
Yeah.
I never did
Saying
the
that you can
mini quiz when you see like part 1, like that one.
Oh, okay. You can do that.
Okay, so how I did it in the calculator was all I had to do is I plugged in at different x values that I want, and then that gives me the y, and then and then just do the normal, normal thing like this.
We need to round to the nearest thousand.
They're giving you the point. So basically, what this would do is if
Yeah,
they
like
give you
class participation
this
points, if you just gap them.
and then not
Okay.
this one,
Well, then you have some error in there then.
this one.
Because it should be right within 3 decimal places. That's what they're going to expect on the AP exam. So if you're rounding somewhere earlier in the question, then
0.
That's what's going on.
Right.
Did you get my agreement
So you do the y at 0.
I don't remember.
The
if I
So you're
did.
saying you did that, you said 0.
Well, today was the first day I asked for it, so if you didn't turn it in today, I don't have it.
Because,
I only have one
so
or two
it's
sentences.
starting at -1. And if you're doing a right read on sum, you can't do -1 because that'd be a left read on sum. No, so
So
you,
you go from 0 to 5.
no, because this is 5 sections. If you go from -1 to 4. That's not how like,
You go 0, 0 to 1, 1 to 2, 2 to 3.
if you do a left read on sum on this, you just take 0. But if you're doing a right, you take 1. Okay. So on this one, so you're, say if you were splitting up
I should have changed the.
8. Yeah,
I see what you mean.
I think.
So if it was a left read on, you plug in -1 to 3, but since the right one, you plug 0 to 4.
Yes,
Could you check if you have mine?
but it's kind of
I will check, but I'm
hard.
pretty sure I
Like
don't.
it's easier when it's like this, so you can actually
make sure
visualize
that
it.
part of the difference quotient. You should be taking the derivative of the numerator here with the denominator left alone. Looks like you took the derivative of the numerator and then left the numerator left one or something.
No, I get it. 10.
On this one, I thought you realized that this was, if you recognize that this was the reason, it should be one of the first, or not the first for everybody, but one of the mini quiz questions today, you guys could have changed that to a trig identity, and then it should have just been one you had memorized. You didn't even have to do the difference quotient on it, if you recognize that.
I got that.
If you didn't think of it that way, you might try it again that way. That's why I said you want to have those things memorized.
Mine's
The main call, so I just tried to do it like that.
That's what I did. If mine was cosine over sine. It was just like the opposite. Yeah, that was this is nuts.
Okay, I have to go.
Okay,
See you, Mr. Townsend.
Good luck.
Thank you.
On the AP exam, not the soccer game.
Okay.
Mr. Townsend, can you put in my Z for the mock exam
Which one are
FRQs?
you doing?
Oh,
Can I put in a Z for you?
No, no, no.
I checked that. They weren't scored in there.
number 6?
What do you need?
I checked the scoring in AP Classroom.
Because I took pictures of all my work and put them in.
How do you know how many points you earned on the
You did
FRQs?
this
I
one.
have it in my folder.
So you scored them and wrote it on your piece of paper?
Yeah.
Okay. Well, okay, I didn't see that.
You want me to turn this in?
Yeah, just let me see it real quick. And then, see, like, right,
Cause I have them all in like.
Because
which one did y'all do?
0 to 2.
0 to 2. 2 to 4. 4 to 6. 6
Third
to 8.
period FRQs. See, like, when you score it, if you click how many points you get each right with each one, where it showed you the scoring,
2 to 4.
you know what I'm saying?
4 to 6.
Huh? Like
Sorry?
when you went to FRQ1, box A, and it says like, here's the answer, and you could get 0, 1, or 2 points or something. If you actually click those boxes, it scores them. And so then I can see like how you did overall on the FRQs, and you didn't
Oh.
do that. But you did it on your paper?
Yeah, I put them on paper.
Okay. And how many did you get? 38? Okay, so 38 would be almost in the, or no, it would be in the 4 category.
Okay.
The 38 part of it.
Okay.
Okay, I'll fix it. So I didn't verbalize this again today because I feel like you should have already done it by now. But remember the Delta Math corrections, if you wanted to up your score at all, I told you that I didn't mind if you did that right away or not, but it needed to be done before the AP test. Since I won't see you again before the AP test, this is the last verbal reminder I can give you of that. So.